In this lesson, we're going to learn the first method of solving what we refer to as a system of equations with two different variables. Now, a system of equations is simply going to be a set of two or more equations that we're trying to find the values of the variables that will make all the equations true. Now, let's keep in mind what the purpose of one variable equation is, like the value of the single variable x that would make this equation true. So obviously in this situation, we would subtract 3 from both sides to get 6 on the right. And now if we have 2x equals 6, we could divide by 2, and we're left with the value of x equals 3. Now supposedly that's the value of x that's going to make the original equation true. But we should always check just to make sure that it works. And so notice that if we plug in 3 to the left side of the equation, then 2 times 3 gives me 6, plus 3 is in fact 9. So sure enough, this is true. And so when we're solving an equation, that's what we're trying to do. We're trying to find the value of x that makes the equation true. Well, the same can be said for any equations that have 2 variables or even 3 variables. Okay, we're now simply asking what values of x and y will make that equation true. So let's take a look at this first equation up here. It says solve x plus y equals 6. Well, notice there's a lot of different values that are going to add together to give me 6. But I know that the value of x and y that will add to give 6 is going to be a solution. So since there's a lot of them, we could just start coming up with a few. Obviously, plugging in 0 for x and 6 for y would be 6. If I add 1 plus 5, that would also be 6. 4 plus 2, or any of these values will combine to give me 6. So 4.3 and 1.7, 97 plus negative 91. So all of these should add to give 6, so we should realize that if they're both x's and y's that give us the solutions, then these are actually ordered pairs on a graph. We can plot a few of these. We could plot 0, 6, we could plot 1, 5, we could plot 4, 2, we could plot any of these values. And notice that when we plot all of those values, it should form a line. Well, that should make sense, because if we put this into slope-intercept form, this would be y equals negative x plus 6, which is a linear equation. Let's take a look at another one. Let's say that we were to solve this equation over here, where we subtract 2 values, and it should equal 2. Well, in the same situation here, we've got a large number of values that are going to work. In fact, an infinite number of values. So perhaps we choose 6 and 4, because 6 minus 4 equals 2. Or maybe we choose 5 and 3, or any of these values that are going to subtract to give 2. 0 minus negative 2 gives me 2. 4.3 minus 2.3 is 2. Negative 81 minus negative 83 is 2. It doesn't matter what values you pick, as long as the two values subtract to give 2. And again, if we were to plot each of these values, we would see quite a few answers as well. And therefore, this is going to form a line if we connect all of the values that end up working. So this method of solving a system of equations is basically to graph the two different equations and see if there's any x and y that make both equations true. So notice that the green table over here shows us some of the x and y values that make the equation true, while the red one also shows me some of the equations that make the red equation true. But what we should realize is that there's one point right here where they cross, namely 4, 2, that's going to make both of the equations true. That is the solution to the system of two equations. So a system of equations is nothing more than two equations or more equations where we're trying to find out the values of the variables that make the equation true. Now, when we look at a graph, okay, we want to determine how many solutions a system of equations can actually have. Obviously, in the last example, we saw that there was one solution because the two lines happen to intersect and therefore give me a point of intersection, a single point of intersection. But it's very possible that there are no points of intersection and therefore no solution. So we could have zero solutions if the two lines happen to be parallel to each other, if the two lines never intersect. And the only way that would happen is if we put both of the lines in slope-intercept form and we realize that they have the same slopes. But now the question is, could we have a situation where we get two solutions or three solutions or five solutions? And you should realize that the only way that that could happen is if the graphs curved around and hit the other graph multiple times. But since all of these equations are going to be lines, lines don't curve. So the only other situation that can happen is that we get an infinite amount of solutions. And we could see that again if we see that the lines are in fact the same line, if they happen to be on top of each other. And we could see that again if we end up putting them into slope-intercept form in order to graph, and we see that they are in fact the same exact equation. So now if we end up heading down, if we want to graph and solve a system of equations by graphing, we're not going to do what we did on the last slide where we just plug in random values and hope that they end up adding to give the correct number. Instead, if we want to solve a system of equations by graphing, we're just going to put each of the equations into slope-intercept form. Remember, y equals mx plus b. And then we're going to neatly graph both of the lines on the same coordinate plane.